So I would like to introduce today a class about extreme statistics, theory, and application in cell biology. And this class belongs to the series of classes that we have presented so far. So what is extreme statistics? And for this, I would like to give the following example. Suppose we start with n particles located at position A at time 0, and suppose the particles are moving inside the domain, and we are interested in the case where you have initially n numbers of particles located at point A. And this particle, for example, they can move by a stochastic equation, which is x dot equals b of x plus sigma of x w dot, where w dot is the Brownian motion. So this is Brownian motion. And b is a deterministic drift. And sigma is the diffusion tensor. For example, we are the case of a pure Brownian motion, which is w dot or square root of 2d, where d is a diffusion coefficient, is a good example. And so those particles, let me draw their trajectory in red. They can move by Brownian motion. And now we have n of them. So this is another trajectory in green. And we are interested in the statistics of arrival at, let's say, the point B, which is the exit point. So then we have, let's formalize the question. We have n particles, so that leads, give rise to n trajectory, x of t, xn of t. So this is a number of trajectories that are generated starting from A up to point T. And we are interested in the statistics of, let's call it tau n, which is the minimum of the arrival time of, let's say, T1, Tn, where each Tk is the first time. This is the first time that the particle, let's say k, reach the boundary. Okay, and the question is, what is the statistics satisfied by tau n? So what can we say? What can be said? What can be said about the statistics? About the statistics of tau n. And so basically, by choosing the minimum time, the main idea of this extreme statistics is that, in some sense, what is selected is trajectories that are going very close to the shortest one. And this is what we would like to present here, at least to discuss, that the shortest path going from A to B is going to be the path that is going to be selected. And this is a very untypical path, because typical Brownian motion, before exiting, they will visit all the domain here. They will basically feel the domain before exiting. But by looking at the time for the fastest one, we are selecting this very unusual path. And so if we are drawing here, for example, the distribution of exit time, which look something like this. So this is a distribution of exit time. Distribution of exit time. Then the time we are selecting, or the region we are interested in, is this very thin region here. And this is what is called the extreme statistics, because it is associated with events that are rare events, but yet those are the ones that we will be interested in. So now let me explain what is the motivation for this extreme statistic, at least nowadays. There is a long tradition of this question back to the beginning of the middle of the last century. But the reason why we were interested in this is because of biological motivation. And now I would like to describe roughly some of them. So first, let me introduce you the classical question that we have been interested in is the time it takes, for example, for calcium ion to flow in a particular structure called a dendritic spine, which is located on the dendrite of neuronal cells. So this is called a dendritic spine. And if, for example, we are interested in what is the time course of calcium ion located inside this structure to escape by a diffusion, that is, suppose at time 0 we have, let's say, 1000 of this particle located here at the center, and they are moving by diffusion. And the question was how long it takes for these ions to escape. So by diffusion, this has been discussed in previous classes, and using, for example, typical numbers, this is of the order of 30 to 100 milliseconds. However, recent experiments have suggested that in some cases, calcium ion can be seen, or at least the fluorescence triggered by calcium ion can be elevated in the order of a few milliseconds, let's say 4 to 5 milliseconds here. And this suggested that possibly the reason for this mechanism is that the fastest of these trajectories, so if we are interested, if we look at the fastest one, then the fastest one can arrive to a specific region to open some channels, and then leading to the release here that I will now add in red, I'll put in red, the release of ion. And this release of ion triggered by the fastest one is an effect of extreme statistics in signaling. Another example is after, so this is case in example 1, which is the case of calcium ion, and the second example is following a photon arriving on fly photoreceptor that have to activate a rhodopsin molecule. Then following this activation of rhodopsin molecule, there is a cascade of chemical reaction that leads to a secondary messenger pathway, which ultimately, this molecule, they have to bind a specific channel. And this channel can be bound, let's say, by calcium, or can be activated by calcium, or by another unclear molecule that may have to do with what is called the phospholipase cascade. But to activate this first channel, then a calcium ion will flow in. And so again, what is interesting is the first messenger, the first ion or the first molecule that will arrive here, that will open the channel. And again, we are left with an extreme statistics, that is the release or the opening of the channel will be triggered by the first molecule that will arrive to the binding site. So again, we are left with an extreme statistics extreme statistics phenomena. Okay, so now let me summarize this with these following examples that we just discussed. So if we consider the case of a dendritic spine here, ions are released here, let's say due to a synaptic event, and the first calcium ion that will arrive to this position here where a ryanodine receptor is located will lead to the release of calcium, which leads to an amplification. So this suggests that the fastest trajectories is the one that will set the timescale of this transduction pathway. Another example is when we have a receptor called metabotopic receptor that is activated, it can lead to the activation of IP3 receptors. And again, the fastest of this IP3 molecule that can arrive here to the IP3 receptors will be responsible for the release of calcium that can induce calcium release. And finally, the third example is the case where neurotransmitters are released following an action potential. So we have now about 2,000 to 3,000 molecules that are diffusing here in the synaptic cleft. So some of them can be lost, but again, the first one that will bind here to a receptor such as AMPA or NMDA receptors, but if we stick to AMPA receptors, it will open the receptors and lead to a synaptic current. So in all this example, the fastest event is the one that is going to define the timescale of the transduction. And there is also a consequence that I would like to discuss now for the application of stochastic chemical reaction. So let me remind that when we have two species that can be described by the classical chemical reaction, which is A plus B that will lead to AB, the forward rate here, K1, so K1 is called the forward rate, and it has been calculated using either the Smoluchowski calculation in 1916, or we use the narrow escape to give an approximation for K1. This is called the narrow escape rate theory. But this calculation assumes basically that, for example, in case of Smoluchowski, that infinity there is a fixed concentration that is maintained. And this leads, for example, to the rate, which is usually proportional to K1A. That is the number of molecules that is going to be generated, like AB is proportional to K1A, and then, of course, it depends on the molecule B. So this is the what's the classical theory said. But if we are considering the case of a transient where there's no particle at the beginning, then the activation, the production of AB can be very different from the one generated by this. And in that case, the K1 of extreme statistics is associated actually not to the K1 of the Smoluchowski, but to a different form, analytical form, which is D, the diffusion coefficient, log of A, and this divided in the geometrical parameter, which was here the volume of the domain. It is associated with the length L of the shortest geodesic. Length of the shortest geodesic. which is the shortest path between the point where, for example, A is released and where the first molecule B are present. And this is important, especially to model transduction, which are transient phenomena. And so I would like now to spend some time to describe how do you find this new law. And the second important consequence is that we cannot use the classical Gillespie algorithm to model transient event. So the classical Gillespie method, which is a method of simulation using a Poissonian rate. So this is a classical simulation method using the Poissonian, using Poisson rate. Then these methods cannot be applied here because it assumes that the production is proportional, the rate of production is proportional to K1A, which is the classical concentration, and then all the statistics is driven according to this rate. But obviously, as we have seen here, this rate has to be modified. Another possibility would be to replace the Gillespie method with this new rate, which requires some adaptation of the method. So first of all, I would like now to start the probability paragraph. So in terms of probability, if we are interested in the probability describing the probability of the fastest event, which is the probability that tau n, let me remind you that tau n here is the minimum arrival time, and we can have in mind the first example of a n particle located at point A that will arrive to point B at the exit. Then the probability that tau n equals t is obviously the derivative of the cumulative, which is probability of tau n less than t. But then, now going back to this, the opposite event, which is the survival probability, which is probability of tau n bigger than t. By definition, since tau n is the minimum, then it means that they are all bigger than t, and since all the time t1 is bigger than t, t2 is bigger than t, and so on. And this means that because they are all independent events, that it is simply the product of the probability, which is tau1 bigger than t to power n. And now we can simply use this in the first equation and differentiate with respect to t. So now let me put this in bracket so that so I'm now going back to this identity here. And so the conclusion is that now the equal term here refers to the first equation. It's simply the derivative with a minus sign. So this is n times 1 minus the probability then tau is less than t, which is to the power n minus 1, multiplied by the probability density function, which is probability of tau equals t. And now this can be connected, for example, for a Brownian particle to the solution of the Fokker-Planck equation. So for example, if the particle is the pure Brownian diffusion, then the probability density function satisfies the diffusion equation. which is dp dt equals d Laplacian p. And for example, if you are in a domain, then dp dt equals 0 if there is no flux on the reflecting part of the boundary, or p can be equals to 0 if there is an absorbing part, as we have described in the previous example on slide 1. And the probability, then tau equals t. So let me remind you the classical result that we have discussed in previous classes, that the survival probability, that probability of tau, is bigger than t. This survival probability is exactly obtained by the integral of px, the probability density function, that the particle is located at position x at time t, condition that it started at position y, and we have to integrate over dx, over the volume. So now it's not very hard to use this identity to show that the density probability function, that is this term here, can be related to the flux. Just differentiate this equation, and then we'll get dp dt and use the classical Gauss integral to obtain that this is the integral of dp dn. And since dp dn is 0 except on the absorbing boundary, then we have to integrate here over d omega a. And this term here can be simply related to that one, because it is exactly 1 minus. So which means that all of this equation here, all the terms here, can be calculated explicitly once we know how to solve equation star. Okay, and so I would like this can be solved, for example, in dimension 1. In higher dimension, this is a little bit tricky, because then we need to look at the time it takes to escape through a small hole, and we are back to the narrow escape theory. I'm not going to treat this in this class. I will give a reference where we have done it, and probably postpone it to another class. But so if, suppose you have an interval of 0 L, or let's say half a line, and so you are interested in how long it takes for a particle, or an ensemble of n particles located, let's say, at position y, to escape either at 0 or at L, or here the same, we start at position y, and the particle, they are making a Brownian motion, and we're interested in the first time when we have n of them, so the first out of n, to escape at L. And so this, for example, in the case of an interval, the solution px of t can be obtained by the method of separation of variable, and is written as, in terms of eigenfunction, as the sum of exponentials. So suppose the diffusion coefficient here equals 1, otherwise we just have to add it. So we have lambda n squared t cosine lambda n x multiplied by cosine lambda n y, where lambda n is the classical eigenvalue, which is pi divided by L, n plus 1/2, where n is the integer. Okay, so using this, the solution of this equation, we can use that into this integral, and then calculate all the terms in this extreme statistics. I would like, before showing you an explicit example, I would like now to draw your attention. There is also an interesting question, which is the second arrival time. So the second arrival time second arrival time. That is, suppose you are interested, so you have the minimum time to arrive. So this is, let's say you start in A and you arrive in B, and this is the minimum already for n particles. So this was the minimum from this trajectory, you got the minimum for n. Then you wait that this happen, and then you look at the second one, which is you look at the minimum of the remaining particle. So now you have one has escape, and you have x1 and xn minus 1. And you are interested in the first one, in this one to happen. Why this is important? Because, for example, you can have channels on the surface of a cell which has two binding sites. And thus, you are the first binding site should be, of course, bound by a particle, by, let's say, calcium ion. But then you have to wait that the second one is also bound so that you can have a flux or outward flux of particle outside. And it's a little bit more complicated than that, because sometimes this particle, the first one, can escape before the first one has arrived. But suppose this is not the case. Suppose it stays, and then what we need to calculate is the distribution for the second ion to arrive. And I'm just going to give you the principle. The principle is to look at the two events. That is the probability that tau2, the second, has arrived at time t, can be calculated from the probability that first, indeed, tau2 has arrived at time t, condition that tau1 has arrived at time s, multiply by the probability that tau1 is equal to s, and then we have to integrate over all time s between 0 and time t. It's a little bit more complicated in the case of Brownian particle, and there is an extra term, so let me explain what happened in the case of Brownian particle. So if at time 0 they are located, let's say, here at the one extreme part, and we are interested when the particle will arrive at this extreme end, let's call it B. Then when this happens, let's say the first ion, the first particle, has already arrived. That is, suppose you have the first ion that is already here. But then, at this time, there could be a distribution here of ion. That is, they haven't just waited at the other extreme at a position A, but they may have already moved. And so this implies that we cannot just approximate their distribution as simply Poissonian. And then in here, there's an extra term that has to do with the distribution of their position. I'm not going to discuss it in here, but just to say that this extra term can be calculated, and it is the integral of from 0 to L of the probability that the particle is located at time s at position x, and then we have to integrate over all x dx. And since we have n particles, this is to the power n. Or if we are left, let's say, if one has already arrived, then we are left with n minus 1 particle. So this is n minus 1 here. Okay, so now we are ready to look at a precise calculation to indeed calculate not this probability distribution function, which we have discussed here how to calculate, but now the average. So let's move on now to what is called the mean first passage time. So we are interested in calculating now the mean, that is, what is the average of the time tau when you have n particles. And this average time, maybe I will do that in the next lecture. I would like in the next lecture to calculate tau n explicitly, or at least asymptotically. How do you calculate tau n asymptotically, at least for an interval 0L or half a line? That is the escape from position L when the particle started, let's say, at position Y. And for this, what we need is to use what is called the short time asymptotics of the diffusion equation. So we need to look at the short time asymptotics of the diffusion equation. So what is this? So suppose we are looking now in dimension 1 at the solution of the Fokker-Planck equation, which is simply the diffusion, which is dp dt equals ddp dx squared with d diffusion coefficient, and with the boundary condition that p equals 0 at 0 and L. And so what is the solution of this equation, for example, for half a line? Well, for half a line, this can be obtained by just taking the image of the solution of the fundamental solution. So this is exponential of minus x minus y squared divided by 4 dt. And then there is 1 divided by square root of 4 pi dt. So this is the first term, minus, so that the solution will vanish. So this is this density function, minus the exponential of the same thing, except that the point y becomes minus y, so it becomes x plus y squared divided by 4 dt. All right, and so this is the equals this probability density function p x at time t. This is transition probability from a y, the particle started at position y at time 0. And in the case of an interval, we have to actually we need to sum an infinite term. So let me write the expression for the case of the interval p, the transition probability from y to x during time t can be written as a sum for n in z. So this is the sum of a similar expression, except that we have a shift of the lengths of twice the size of the interval, which means that we have exponential of minus x minus y. And now we need to be careful here. This is plus 2nl squared. And again, this is divided by 4 dt. 4 dt. And with the same minus the same quantity, so I'm not going to rewrite it, but here we have to add the equivalent of this term here with a plus. So again, just to make sure that it is clear, here we have x minus y, right? Okay, and in here we have to add the same term as in here with a shift of 2nl plus the normalization here in front. Okay, so I'm going to stop here and resume in the next class about this extreme statistics, how we are going to continue this calculation and how we are going to use this explicit representation using this short time asymptotic. Short time asymptotics, you can see here that when t is small, this solution converges to the delta Dirac because of the position of the t, which is very different from the expansion on the eigenvalue, which is more valid for long time asymptotics. So I'm now going to finish with some another example and some references. So let me just comment on this. So this is the case of a Brownian particle in dimension 2, and the particle is escaping, and when we are looking at the statistics of the extreme, we see that again the time is very different from what is expected just by dividing the time by n, because what comes here is actually the log of n. And this is the comparison between simulations and the theory. And again, so this was in dimension 3. And in dimension 2, similarly, we have this log of n. So here, actually, what is missing here is a square root. So what we should be seeing here is square root of log of n. While here it is just log of n, and this is in dimension 2. And again, the shortest path that is selected, the typical path for the extreme statistics is associated here to the shortest path. And again, the stochastic simulations agrees nicely with the result of the asymptotics that again I'll describe in the specific class with the calculation in dimension 1. So the typical example of this probability distribution function, the histogram, can be found here. So here we took, for example, n equals 5 particles. And you can see that when you go to n equals 50 for the probability distribution function of the first one to arrive, there is a shift in the arrival time compared to n equals 5. And another example here is for the case of the probability distribution function for the time for the second ion to arrive. And so this is before the correction. So I explained in the previous slides that there is a correction because Brownian particles, after the first one has arrived, can have a distribution inside the domain. And so this is after the correction. So this shows actually that the correction, the effect of the correction is not that drastic. And another example is the case of fertilization, where spermatozoa, once they are arriving here at the beginning of the uterus, they have to find the eggs, which is a small target that can be hidden here into the fallopian tube. So here we have looked at the question of how long it will take for the fastest spermatozoa to arrive to this important region here. And so if we look specifically at the shortest path, so this is explained here in this distribution. So we take the first one in the distribution, we could see that all the rays, so this is in the model where spermatozoa are just shooting, that is between 2 points A and B, we assume that the motion is a constant velocity until the sperm arrive here to the boundary, where the motion can be reflected with a random angle which is taken uniformly distributed. And so what the simulation revealed is that the trajectory are concentrated along what we have called this optimal trajectory, which satisfies the associated control problem. And it seems that the trajectories here are made of 2 lines, and this corresponds to the shortest path for the associated problem to find here this region. So we had these 2 regions here that are symmetric, A and A. I'll give a reference to this example now. So this, if you are interested about the search for a small egg by spermatozoa in restricted geometry, this is a work that has been published in 2015, and these are the exact reference. For the work about the calculation, I'll refer to this archive article where we have done the calculation in dimension 1, 2, and 3 with a small hole. The case in dimension 1 was already treated, but we looked also at the distribution of the second ion and the effect of the interval when we have a distribution of the particle inside. And finally, we discuss in this article posted on bioRxiv the general consequences of having many particles, and we call it this redundancy principle, which says that when we have many particles, the first one to arrive is actually driven or uses the optimal trajectories, and this allows to define the timescale, a much reduced timescale for transduction processes. So thank you for watching this video.